Okay, first, before we jump into factoring, I want to talk about something. Okay, let's start off by doing stuff that we already know how to do. It's not hard. If I want to multiply these factors together, how might I do that? I got three things here. Foil. Okay, foil. I got three things to multiply, so I can only multiply them in pairs. So the suggestion is let's foil first, and then maybe after that distribute the two. Okay? So we'll take these guys, and they're going to give us, if I foil this out, I'm going to get what? X squared minus 3x plus 1x. Now what's that combined to? Okay, so we'll just combine the O and the I into one term. And then finally? Okay. And then I've got to distribute it too.
Just like that.
Right? So what do I get?
2x squared minus 4x plus minus 6.
Okay. That's simple. That process of going from here down to here is what we call expanding. Okay, expanding, multiplying, that just means we're going to take a bunch of factors and we're going to multiply them out, and we're going to go from factors to an expression. So we started off with a bunch of factors because factors are just things that are being multiplied. That's the definition of a factor. So we go from factors down to some, in this case, a polynomial, but we'll just call it an expression. Okay? That is easy to do. You're all good at that. We've done that for years. It's no big deal. What's a little bit harder to do is the reverse process. If we want to start off with some expression, so we're going to start here, and we want to break it apart into a product of factors. Okay, that's factoring, and that's what we're going to work on here for a few days. It's inherently a little bit harder to do. It's easier to expand these things by distributing than it is to undistribute. Okay, but it's not that big a deal, as you'll see. So I'm setting the stage here. We're going to practice starting with stuff like this and breaking it apart into a product of factors. Now, why are we doing that? Well, there's a good reason for this. The reason we're going to do this is because we want to be able to solve equations. Solve quadratic equations in this case. Later on, next chapter, we'll solve bigger equations, polynomial equations that are bigger than quadratics. But for now, we're just going to do quadratics. Now, when we solve equations, we're gonna need to do some factoring, and so let's first talk about the factoring part just briefly, and then we'll kind of put that into the context of why are we doing this, and then we'll practice some more factoring. First of all, let's look at what we just did. We know that if we took something like x plus m times x plus n, we FOILed that out to get this answer, x squared plus nx plus mx plus mn. Well, if we combine like terms there, we get an x squared term. We get these two x terms that we added up. Remember, we got a negative 2x, I think. If I combine those two terms, isn't that the same thing as saying the quantity m plus n times x? If I undistribute an x, and that's, by the way, factoring. If I pull an x out of each of those two, everybody see that connection? This stuff goes together right here. Okay? Plus m times n. Okay, so if we were to start with something like a quadratic expression of the form x squared plus b times x, where b is just some number, plus c, we're going to think of that as being, our goal is to try to unfoil that. So we're going to think of that b as being something like an m plus n. It's going to be a sum of two numbers. And that c that we're trying to break apart is going to be like a product of two numbers, like an m times n. Okay? So we're going to look for what we're going to call magic numbers, I guess, for lack of a better word. So when we see stuff like this, this is the factoring pattern that we're going to use. Okay, we're going to try to break it apart, see if we can spot that kind of connection where we can think of two numbers that are going to multiply together to give us a number c, and are going to add together to give us this number b that we're starting with. And it won't always work. A lot of times it just simply won't work. We'll have to try something else, which we'll talk about later. So once again, here's our pattern. If we FOIL this, that's what we get, right? First, outside, inside, and last. Okay? So if we collect the like terms, this is what we got. And if we make this comparison, I know I'm probably overdoing this maybe, but I just really want to make this point. If we collect the like terms like this, and we think of our quadratic expression that we're going to break apart as having to fit this kind of a pattern, we can see then that the c equals the product of the two numbers that we've unfoiled, and b has to equal the sum of the two numbers. Okay. Now let's maybe before we move on to talking about why this is important, let's try doing a couple examples like that, and you'll see it's not that big a deal. What if I ask you, and I know you've done this before too. What if we want to break this expression apart? Okay, we want to try to break this apart, unfoil it. What's that going to look like? If I'm unfoiling it, first times first gave me an x squared. So what are the first terms, obviously? X's, sure. Okay, but we need the magic numbers then. We need the numbers that now multiply. You know, we might have called this m and n. M times n has to equal c, right? And m plus n. Oops, I got it backwards, didn't I? Hang on. Got it backwards. Whoops. That's what I wanted to do. So m plus n has to equal 5, and m times n has to equal 6. So what are the two magic numbers then? 2 and 3. Good. And it doesn't matter what order I put those in, right? It makes no difference because I've broken this apart. I've broken this apart into a product of factors, and we know that multiplication is commutative, right? It doesn't matter the order in which I multiply things. X plus 3 is this times x plus 2 is the same result as x plus 2 times x plus 3. When I FOIL them out, I'm going to get the same answer either way. So it makes no difference. Okay, so I mean, you're familiar with that process. Let's maybe try one more of those. We're going to start today. We're only going to deal with simple factoring patterns where we don't have a number other than 1 in front of x squared. So if we thought of this as being in the form ax squared plus bx plus c, which is our standard form we talked about the day before yesterday, a is equal to 1. Now, we'll come back later and look at some examples where a is not equal to 1, and that gets a little trickier, but it's not horrible. So how about this one? Okay, now I want to, because a is equal to 1, when I'm unfoiling this, first thing I always want to do, I want to set this template up. What are the first terms? X's. So we always want to write that stuff down first, because we know that if it factors, it's got to look like that. Now the magic numbers. They have to multiply to what?
-6 and 2.
They have to but that's the answer, but they multiply to what number? Negative 12. Add to negative 4. So what would they be? Negative 6, positive 2. Now there is, and as we get into some more examples, we can talk about some little tricks. And the little tricks, yes sir?
Does it matter where the 6 and the 2 go in the parentheses?
Doesn't make any difference. Doesn't make any difference. Either or. Makes no difference. There are some little, like I said, some little tricks we can play to make this process a little bit easier. For one thing, we can always play a little sign game here. We can ask ourselves now, we know if the numbers are going to multiply to negative 12, if they multiply to a negative, what can you tell me about the signs of the two numbers?
What factors?
Say it again? One positive, one negative. Okay, they're opposite signs. They have to, because the only way I can get two numbers to multiply to a negative is if I have an odd number of negatives. If I have two numbers, then one of them has to be negative, right? So I get a negative and a positive. Now, one thing that I like to do, you don't have to do this, it's up to you, but it's a way to organize your thinking, maybe at least at first. I like to put the number that's going to be bigger. If I know which sign is bigger, I like to put that first. Okay? Which number is going to be bigger here? I'm hearing a little bit of both. Now, there's a way we can tell. If the numbers multiply to a negative, they're opposite signs. If they're going to add to negative 4, what does that mean? Which of the two numbers, the negative or the positive, must have been bigger? If I add them up and I have some negative left over. Because negatives and positives cancel each other, right?
Yeah.
Must have been the negative, right? And how much bigger was it? 4. Do you see the point of that? If I add, now think we know the answer to this. You guys have already told me the answer is negative 6 and positive 2. When I add negative 6, a fairly big negative number, to a small positive number, positive 2, I'm left with negative 4, because that's how much different those numbers are. 6 and 2 are 4 apart, right? So the fact that this is negative here tells me that the bigger of the two is going to be negative, and it's got to be 4 bigger. That helps me find it, right? I know that that's, in this case, it's pretty simple because the numbers are so small. But what if the numbers were a lot bigger? Because they will be in certain cases.
Start doing factoring.
Then it's nice to know, are they close together or are they far apart? If this number here is small, that means the two numbers are close in size, the positive and the negative. And I can focus on those. So, in this case, it wasn't a big deal. Okay, let's try one more, or maybe two more. Okay, first terms. Okay. Now, people are already telling me some answers. I mean, you guys are smart enough that you're going to see these right away, but pretend this is a little harder than it is. Let's just play that sign game again for just a second. If the two numbers multiply to positive 63, what does that tell me about the signs?
Either both positive or both
Okay,
negative.
same sign. We don't know if they're both. That by itself, if I ignore this middle term, the fact that they multiply to a positive number means that they're either both positive or both negative. In both cases, I'm going to get positive products, right? The fact that they add to a negative, though, tells me
They're
both
both negative.
negative. Okay, so I already know the sign before I even start. Now, what are the numbers that multiply to 63 and add to 16? Yeah. Okay, makes sense? This is no big deal. You guys, I know you've done this before. Okay, so you're already, you know this pattern. You've done it before. Maybe you might have not have used it for a while, but now it's all coming back to you. All right, let's talk about why it is we do this. Okay, the reason we do this is because of something called the zero product property. Now, I want to use, some of you have probably heard me do this before, but I want to warm up before we do this a little bit. I want to have you guys do just a little arithmetic, because we're going to be doing a lot of arithmetic, a lot of multiplication when we're doing this factoring stuff. So, in your head, please multiply this stuff out for me, okay? Let's multiply 12 times 3, okay, times 11.457, times pi, times 1,100,597,000, 419.9. You with me?
No.
Okay. Times 0 equals
Zero.
0. Okay. Doesn't matter how complicated the other factors are. If I'm going to get an answer of 0, well, anytime I multiply by 0, I get 0, right? In fact, is there any other way that I can multiply things together and get a 0 answer? No. That's the only way. Only way it can happen. So, the zero product property here is useful for us lots of times. If I want to know, for example, when, say I've got an equation like this. Say I've got an equation like x squared plus 2x not equals. For now, let's just do this. Minus. No, that's not what I want. If I've got an equation like that, knowing the values of x, the value or values that's going to make this complicated expression turn out to be 0, would be hard to do, right? I don't know what values. If I plug in 0 for x, I'm going to get 0 plus 0 minus 24 equals 0. So the 0 value for x didn't work, did it? Can you think of a value of x that might work?
24.
No?
Oh.
Doesn't matter if you can or can't, because normally you wouldn't be able to. Normally it'd be way too hard to even try. So we won't even mess with, don't even bother wasting time on it. Trying to arbitrarily pick values of x that are somehow going to add, make these terms add up to 0 would be really difficult to do. However, if we could somehow break this thing apart into a product of factors rather than a sum of terms, that question would be a lot easier to answer. If I could instead write it in that way, that might be useful. Okay, now we could do that though, couldn't we? We could unfoil this one by factoring. What two numbers multiply to negative 24 and add to positive 2?
Negative 6 and 4.
No, let's be careful there.
6 and negative 4.
I'm going to have opposite signs, right? Because they multiply to a negative, and the bigger one's going to be positive. So what would they be? I think I heard it.
6 and negative 4.
Okay, that's a little easier, isn't it? Okay, by this concept of the zero product property, which we'll look at the technical definition in a second, but you just recognized what it was. When I gave you a whole string of complicated factors being multiplied together, the answer would have been hard to find until I multiplied by 0, because multiplying by 0 was it made my answer equal to 0, right? So the zero product property then just says, if I multiply a string of factors together and get a 0 result, the only way that could happen would be what? What's the only way that the product of the factor x plus 6 times the factor x minus 4 could equal 0? There's only two possible things that could be going on. Kyle's got an idea. Negative, say it again.
Negative 1.
Not negative 1.
0.
What would the value, ignore even what these factors are for a second. I've just got this times that. Right? I've got left hand times right hand. If they're going to equal 0, what must the value of left hand or right hand equal? 0. Yeah. The values of one of those two factors has to equal 0. Either x plus 6 equals 0, right? Or x minus 4 equals 0. Because the product of the two is 0. And by the zero product property, that's the only way that could happen. Right? So either that's true, or that's true. Now, those are easy equations to solve, right? This one's pretty hard. It's quadratic. But these are linear. They're simple. When is x plus 6 equal to 0? When x equals negative 6. Or when is x minus 4 equal to 0? That's it, right? So you get the idea. That's why we're factoring. It's an important skill, but this is why. We factor because we want to be able to break big expressions up into small pieces and use that zero product property to find the answers. These are the values, -6 and +4, that would have worked in this original equation. We could test it out and see. If I put in +4, I'm going to get 16 plus 8, right, is 24, minus 24. What do you know? It's 0. What if I put in -6? What's -6 squared? 36. Plus 2 times -6, what's that? Does that work? 36 minus 12 minus 24? Of course it does. Yeah. So those are the two values. Okay? So there's our zero product property. If A and B are real numbers, or algebraic expressions like we just dealt with. They could be, x plus 6, or x minus 4. Then the product of A times B can only equal 0 when either the first factor is 0 or the second factor is 0. Okay, that's it. If the product of two factors is 0, then at least one of the two factors had to be 0 itself. Could this apply to more than two factors? Sure. If I have a product of 5 factors that equals 0, then that means that one of those 5 factors had to be 0. So we have to look at all those possibilities. Those would be the solutions. Okay. I think maybe we're ready to go. Right? So what we're doing here is we're factoring, setting the factors equal to 0, and solving the individual factors. Okay? Let's call it quits there and go practice a little bit, and we'll pick this up tomorrow. Now,